This is problem 780. It's on page 357. Consider an aircraft powered by a turbojet engine that has a pressure ratio of 12. The aircraft is stationary on the ground, held in position by its brakes. The ambient air is at 27 degrees Celsius, 95 kilopascals, and enters the engine at a rate of 10 kilograms per second. The jet fuel has a heating value of 42,700 kilojoules per kilogram, and it is burned completely at a rate of 0.2 kilograms per second. Neglecting the effect of the diffuser and disregarding the slight increase in mass at the engine exit, as well as the inefficiencies of engine components, determine the force that must be applied on the brakes to hold the plane stationary. Now, before I read the last sentence, note that it's saying neglecting the slight increase in mass. What they're saying is there's a little bit more mass coming out the back because of the fuel addition, but just neglect that part. We'll just consider the air flowing through. The last thing they say kind of highlights the fact that this author writes books by cutting and pasting, basically. And it says, account for the variation of specific heats with temperature. That's wrong. We're supposed to assume constant specific heats. He doesn't have any method in this book for accounting for variation in heat capacity. We'll do that, like I said, once we get to 320. But as I said, that's just a copy-paste error. We can still solve this problem. We just need to assume constant specific heats. So let's begin again with the cycle diagram. And I won't draw a figure of the actual system. And I'm not going to bother with a PV diagram because really it's the TS diagram that's more important. So let's draw the ideal jet engine cycle. Looks about like that on a TS diagram. State 1 is here. Now state 1 is the inlet to the engine. So at this point it would be good for you to find the TS diagram for the jet engine cycle. And that's on page 311. And it will help because on page 311 at the bottom, not only is the TS diagram there, but a schematic of the engine is there as well. So you can see how the air moves through and what state we're talking about. So this state 1, that's all the way on the left-hand side where the air is entering the engine. The first thing that it encounters is a diffuser, but notice what they said. They said neglect the effect of the diffuser. Now what would the diffuser do in the real world?
Compress the air before it reaches the compressor.
It compresses the air before it reaches the compressor. It changes the flow area, it increases the flow area, which makes that air slow down as velocity decreases. Okay, now that kinetic energy goes somewhere. Where does it go? Into flow energy and thermal energy. Okay, so yeah, it compresses the air. But they said to neglect that, so basically state 1 and state 2 are the same dot on this cycle. Make sense? State 3 is the exit of the compressor. State 4, well, state 3 to state 4 is the burner section where heat is added. Okay. State 4 to state 5 is the expansion through the turbine. And then state 5 to state 6 is the expansion in the nozzle. Okay. So the magic of all this really happens right here in the nozzle. You take fluid, basically hot air, that's at a high pressure and high temperature. You expand it through a nozzle, converting some of that energy into kinetic energy, and you saw the effect of that kinetic energy on the Mythbusters video. It's huge. Okay, and of course Q out actually occurs in the atmosphere, but we'll draw it here. Now we were given some information. We were told, let's see, that the air comes in at state 1 at a temperature of, what was it, 290? What they said? No, 27 degrees Celsius. So I'm just going to put the temperature down in Kelvin. So let's say 27 plus 273, yeah, they just made that a nice round 300 Kelvin. Okay. Now let's see. Since state 1 and state 2 are essentially the same, all we need to do to solve this is move from state 2 to state 3 first, 3 to 4, 4 to 5, and so on. Okay, so we're just going to walk around the cycle diagram again and try to solve everything. Now we were given some other information. We were told the heating value of the fuel and the fuel flow rate. So let's jot some of that down. The heating value of the fuel is 42,700 kilojoules per kilogram, and the mass flow rate of the fuel is 0.2 kilograms per second. Okay. Lastly, the pressure ratio was 12. And I thought there was something else. Oh yeah, here we go. the mass flow rate of the air is 10 kilograms per second. And the pressure of the air, so the pressure at state 1 is 95 kilopascals. I think that's the last bit of information. Did I miss anything else? I think that's it. Okay, so how are states 2 and 3 related? Just look at the TS diagram. How are they related? They're isentropic, right? It's a vertical line. And so we should be able to use an isotropic equation. What one should we use? Well, generally what we're trying to do in all these cycle problems is find the temperature. Once you find the temperature, you pretty much solve the problem. So we'd like something that would relate the temperature at state 1 to the temperature at state 2. Okay? So an isotropic equation would work, right? In fact, the isotropic equation would look something like this. The temperature at state 3 over the temperature at state 2 is equal to the pressure at state 3 over the pressure at state 2 to the K minus 1 over K. Okay, so there's our equation. Now you might look at this and say, well, great, we know the pressure at state 2 because it's the same as the pressure at state 1. What's the pressure at state 3? That's where the pressure ratio comes in. We don't really need the pressure at state 3 because really this is just the pressure ratio. But for the sake of calculating it, let's go ahead and do it. P3 equals P2 multiplied by the pressure ratio. So P2 we know is 95 kilopascals, and the pressure ratio is 12. So plug that into your calculator, please, and just let me know what the pressure is in state 3.
1140.
That's right, 1140 kilopascals. So now we know the pressure in state 3. Let's just jot it down. In fact, notice that the pressure in state 1 and the pressure in state 2 happen to be the same because we're told those are the same states, but that's also the pressure in state 6, right? Because basically the inlet and exit pressures are the same. Now in general, in a jet cycle problem, the pressure at state 2 and 5 are not the same. Those are intermediate points. State 2 is between the diffuser and the compressor. And state 5 is between the turbine exit and the nozzle. Okay, so there's no guarantee that those pressures are the same. But always the pressure at state 1 and state 6 are the same. That's just atmospheric pressure. And the pressure at state 3 and state 4 is the same. So once we've calculated the pressure at state 3, let's just jot it down over here. P3 is 1140 kilopascals. Then we also have the pressure at state 4. Now look at your diagram, your schematic of that engine, and you'll see that 3 and 4 are both just in the burner section. That's just an open chamber where fuel's being added. Okay? All right.
Is the ratio also true between 4 and 6?
Yes, basically the ratio, this is the high pressure side of the turbine, or the jet engine, excuse me. This is the low pressure side.
All right.
And you'll notice if you look at your schematic, 1 and 6 are outside of the engine. They're both just in the atmosphere. Whereas 3 and 4 are in the burner section, which is just an open chamber. Make sense? Okay. So now we should be able to find the temperature in state 3. It's just equal to the temperature in state 2. You see all I'm going to do is move that there, so let me just put in the numbers. The temperature at state 2 is the same as the temperature at state 1. It's 300 Kelvin. The pressure ratio is 12, and we need to raise this to the power of 0.4 over 1.4. Okay? Sorry, my exponent is pretty large there. But that's the exponent on that ratio. When you do this, you find that the temperature is 610 Kelvin. So that's the temperature right here. So let me add it to this diagram. Should be consistent. I have no particular reason for using dashed lines one time and solid lines the next. Now how about from 3 to 4? What's the relationship there? Any ideas?
It's an ideal gas, is what we're going to do.
It is an ideal gas, but notice that usually in the Brayton cycle problems and the jet cycle problems, we don't end up using the ideal gas law very often because we don't typically have volumes. We don't have specific volumes. So that's not going to help us. What else do you notice? Notice in the diesel cycle and the Otto cycle, and even the Brayton cycle, we use two tricks, isentropic and energy balance. Those are the two things we used, right? So what do you know about state 3 and state 4?
Temperature increase due to the QN.
That's right. QN causes a temperature increase. Basically, we can use an energy balance. Okay, so let's see, what would that look like? Well, help me out with this one. QN is going to do what? Where is the heat going to go?
It'll either go out or it'll be work, right?
Well, ultimately in the engine, but just as it flows in, it's just going to add to the air, right? It's just going to add. So basically, the air coming from state 3 at the entrance to the burner is going to bring in energy, and the heat is going to add energy to that air.
It'll be the difference between 4 and 3's.
Right.
Enthalpies, right?
Enthalpies, good. Did I put those in the right order? Which one will have the higher enthalpy, 4 or 3?
4.
Hopefully 4, right? Yeah. So then how do we approximate this? What do we usually do? CP delta T. There you go. Trying to help you guys learn all the tricks. Okay. So that's our, now, do we know anything about this?
I said energy instead of enthalpy, and that's wrong, and I can't remember why.
Well, enthalpy is, you can look at enthalpy as a form of energy. Because enthalpy really is just accounting for two different forms of energy. One is flow energy, the other is thermal. So you're right, we use an energy balance, and that's what it is. It's just different forms of energy. Now notice, we don't know QN. That's another very good question, Mark. We don't know T4, so how are we going to deal with this?
I thought we knew QN.
We do know QN, but it's given to us in a tricky way. They gave us the mass flow rate of the fuel and the heating value of the fuel, right? So let me ask you a question. If I get jet fuel, forget the flow rate for a minute. If I get a kilogram of jet fuel and I burn it, how much thermal energy am I going to get out of it?
Apparently 42,700.
That's right, 42,700 kilojoules. What if I only burn 0.2 kilograms, then how much do I get?
You get a fifth of 42,700.
Exactly. And so if I burn that 0.2 kilograms every second, then that's the heat flow rate. Does that make sense? So am I going to use a Q dot, a capital Q dot in, or a lowercase q in?
This is specific, so it would be.
Well, what you just described to me, the product of these two is a capital Q dot, right? Okay. Because this is going to be the heating value multiplied by the mass flow rate of the fuel. Now look at the units and you'll see how this works out. 42,700 kilojoules per kilogram, that's per kilogram of fuel that's burned, right? Multiplied by 0.2 kilograms of fuel per second, you'll get kilojoules per second, so it should be a capital Q dot. Okay, so plug that into your calculator, please. What is a fifth of 42,700?
8,540.
Good. 8540 kilojoules per second, or basically 8 megawatts, 8.5 megawatts, which is a decent amount of power. But anyway, there's the power that we're putting in. Now, we don't really want that, right? We want Q in. Now, what's the relationship between these two? Mass flow rate, that's right. So let me write that down. Let me get rid of this, because really now we've transitioned and we're trying to go from state 3 to state 4. So if I write this, it would be Q dot N equals M dot Q N. Wait a second. Which M dot? How many people want to say air? How many people want to say fuel? Good. Well, it's air.
Yeah.
Why is it air? How come? I mean, aren't we talking about heat flow from the fuel? We are, but you have to understand what these things are. What they're talking about. We've already used the mass flow rate of the fuel to figure out the heat rate added to the air. The question now is, how much heat is added to each kilogram of air? Does that make sense?
Yeah.
That's what we're trying to answer now. And so Qn is really how much heat is added to every kilogram of air that flows through there. Okay? So that would be the ratio of Q dot N over M dot, where we're talking about the mass flow rate of the air. So now let's take this 8540 kilojoules per second and divide it by the mass flow rate of air, which is 10 kilograms per second. You see the seconds go away. And basically, I mean, you can all do this in your head, right? 854 kilojoules per kilogram of air. That's the amount of heat that's added to every kilogram of air that flows through the burner section. Okay? So let me make a note of that. This is 854 kilojoules per kilogram. Okay, so now we should be able to calculate T4. In fact, we used an energy balance, and we said, well, we don't know Qn, so we went and got it. So now let's just solve for T4. T4 would be equal to T3 plus Qn over Cp. I just rearranged this equation to solve for T4. That's all I did. Okay. So the temperature at state 3 was 610 Kelvin. The amount of heat added per kilogram of air is 854 kilojoules per kilogram. And the mass flow rate, or excuse me, the heat capacity of the air. Anyone remember the heat capacity of air from the last problem? 1.005. Good job. 1.05 kilojoules per kilogram per Kelvin. So the kilojoules, kilogram go away. And we just have kelvins of change plus kelvins. Put all that together, you find that the temperature in state 4 is about 1460 Kelvin. Okay? I think I started rounding these off at some point. So there's the temperature of state 4. Now, how shall we find the temperature of state 5? Notice we actually have to deal with state 5, right? How are they related? They're related isotropically. Let's see what that does. What isotropic equation do you think we should use?
What do we know about it so far?
We're looking for temperatures, right? So it'll be a T5 over T4. It's not the one that relates pressures to volumes, right? Okay. Which one do you think it should be? Relate temperatures to volume, or do you want to relate temperatures to pressures?
A lot of these don't really have volumes in them.
Go with pressures. Okay, so how would that go? Would it be like this? Does that make sense? I honestly don't have the isotropic relations memorized completely. I can never remember whether they match or not.
That's all right.
Okay. K minus 1 is the only one that matches. That's what I haven't figured out. I haven't memorized which ones are.
Right, right. Well, that's why I let you use your book and just tab the page. Okay. Now we've got a small problem here. We know the pressure at state 4. We don't know the pressure for state 5. And so we can't get the temperature at state 5. One equation, two unknowns. Rats. What else is there? There's something really important. I gave you an equation that said there's an assumption about this type of engine that's really important.
It's the enthalpy change and then the temperature change, right? How they're equal.
Oh wow, we somehow got way ahead in the slides. I don't know how I did that. Good grief. Yeah, I'm trying to come up with, here we go.
You can read a lot of slides. I don't know how to do that.
Oh, fortunately, I'm not saving them.
Okay.
Oops.
Just making sure.
Is it T4 less T5 is equal to T3 less T2?
You got it, that's right. Same thing you said, Mr. Hamilton, yeah. Yeah, I just deleted a bunch of slides, oh well. Yeah, basically, what was that idea based, where did that equation come from?
It was the the specific work of the turbine is equal to the specific work of the compressor.
Right, basically, the whole reason for having this turbine is to drive the compressor. That's the whole reason for having it. And that's counterintuitive because you would think you'd draw power off this fast rotating shaft. That's not where the power to push the airplane comes from. Okay. So you're right. Basically, we used an energy balance and said the specific work output of the turbine goes into driving the compressor. And ultimately what that meant is that the temperature in state 4 less the temperature in state 5 equals the temperature in state 3 less the temperature in state 2. So if we want the temperature in state 5, we can write it as T4 plus T2 less T3. Okay? Now had you add that, so if you're looking at the cycle diagram and this cross section of the engine, you should have this equation right next to it, just so that it's handy. Okay?
You don't measure
311, I think. Wasn't that what we said a moment ago? All right, so the temperature in state 4 we found was 1460. The temperature in state 2 is 300, less the temperature in state 3, which is 610. Gives us a temperature in state 5 of 1150 Kelvin. Okay, so I've got to cheat a little bit again. So now we know the temperature in state 5. Now, how will we relate the temperature in state 5 to the temperature in state 6?
Same thing, because we know
Same.
pressure at 6.
We know the pressure at 6, that's true, but we can't do this again, right?
No.
There's nothing that constrains this to anything else.
Yeah, so we have to do the isotropic.
Isentropic, that's right. We have to do isentropic relationship here. Because notice, now we know the temperature in state 5. If we wanted to, we could find the pressure in state 5, right? And once we did that, then we could use another isentropic relationship to go from here to here to find the temperature in state 6. There is a shortcut. You can simply relate state 4 directly to state 6. Okay? Because notice that the temperature in state 6 over the temperature in state 4 would be equal to the pressure in state 6 over the pressure in state 4 to the power of k minus 1 over k, because 4 and 6 are also related isentropically. Now we do know the pressure in state 4 to pressure in state 6 ratio. That's that ratio of 12 or 1 over 12 or however we end up having it. Okay? Pressure in state 4 is higher, so this would just be T6 equals T4 multiplied by 1 over the pressure ratio to the k minus 1 over k. Does that make sense? All right. So the temperature in state 4 we found was 1460 Kelvin. The pressure ratio was 12, so we need 1 over 12, and 0.4 over 1.4. All right, so if we plug all of that into our calculators, we'll find that the temperature in state 6, got a cheat there too, is 718 Kelvin or so. Okay. Now that's all well and good, but what were we supposed to do? Gotten down and started looking at all the trees and we're missing the forest, right? We've solved it, but that's not what we were asked to do. Well, let's find out. What did they want again? Determine the force that must be applied on the brakes to hold the plane stationary. Before we do that, let me ask you a question. How efficient is this? What's the whole point of having all this thrust developed by the engine? It's to move. Is the plane moving? No, it's broken. It's broke. It's you know, there's brakes on the wheels and stuff. So, what is the efficiency? Well, if I hadn't deleted a bunch of slides, I could show you that the propulsive efficiency N sub P is equal to the propulsive power divided by the heat flow rate coming in. Now you know that there's a heat flow rate coming in. We calculated that a minute ago. What was it? 8,540 kilojoules per second? About 8.5 megawatts. Remember that? This is the specific heat. This is Q dot. Okay. Well, how much propulsion is there? Nothing, right? Basically, the force multiplied by velocity of the airplane is 0 because the velocity of the aircraft is 0. So this is not efficient at all. It's 0% efficient. Now that's not really a surprise. It's not a problem. We don't really expect the airplane to move. We have the brakes on. This is a good thing, right? Of course, we probably don't want to ramp up the engine to full throttle right now. There's no point. You'd just be dumping more heat to get or dumping more fuel to generate more heat to not do anything. So they didn't ask us about the propulsive efficiency because obviously that's 0. They asked us instead how much force is being generated. And that's a different question. Well, let's see. If we want to calculate the amount of force that's being generated,
Did they give us the efficiency?
well, the efficiency is 0. We already know the efficiency is 0 because there's no velocity. Okay. We just want to know how much thrust is there. How hard is it pushing? Okay. Well, I've unfortunately deleted the slides, but it's in your book, and of course these slides aren't going to be copied over, so you can get them off the blackboard. But basically, the force would be equal to the mass flow rate by the velocity at 6 less the velocity at 1. Now, what am I talking about there? I kind of do need this slide, so let me close this and then reopen it. It'll ask me if I want to save. No, don't save. And then let's see. A quick way to get to the downloads. Yeah, there we go. Let's open up the presentation again. We'll go down to the jet engine cycle. Let's see, there we go. And basically, this is an idea from dynamics. Remember dynamics? Remember the horror movie, otherwise known as Dynamics? Okay, basically what happens is the air comes into the engine with a certain velocity and leaves with a much higher velocity. Its momentum has changed. Okay, and because you've accelerated that air, you're just basically, you've got an equal and opposite force on the craft, right, to push it forward. I mean, it's kind of like, you guys I'm sure have rowed a boat before, right? How do you get the boat to go? You grab the oars, you pull, you apply force to the water, that pushes your boat. That's literally what this jet engine's doing, right? Except it's not pushing against water, it's pushing air. It's pushing that air so hard that it's able to fly through the air. Okay, that's what's happening. And basically it's just changing the kinetic energy of the air from the inlet to exit. Now, we have to be careful here because both of these velocities need to be taken with respect to the same reference frame. Make sense? So if you're standing on the aircraft, which would be a really bad idea when it's flying or even when the engines are on, but if you were, okay, then you would be able to measure the velocity at the exit of the engine and at the entrance, right? Okay. Now if you're standing on the plane, the velocity at the entrance would not be zero because the craft is moving through the air, right? And this would be the relative velocity. But if we're standing on ground, then we could take this velocity to be zero, right? Because ultimately the air has to suck in, or the engine has to suck in air, right? So you can get far enough away from the entrance of the craft where you realize that air is stationary and it takes work to get that air into the engine. So this initial velocity coming in is zero, or at least approximately so. Okay. The velocity at the exit of the craft is what we really want. Now what mass flow rate are we talking about here? We're talking about the mass flow rate of the air. That's the mass that's having its momentum changed, right? So that's no big deal. We know that. That's just 10 kilograms per second. But how about the velocity going out of the engine? Well, we somehow need to calculate the velocity coming out of the engine. Remember chapter 5 where we dealt with nozzles? You remember what we did? From 5 to 6 is the nozzle. What we did is we said we could use an energy balance. Q dot minus W dot equals mass flow rate times H6 less, or plus V6 squared over 2 minus mass flow rate times H5 plus V5 squared over 2. Does that look somewhat familiar? Okay, that's just an energy balance. And what we're going to do is apply this to the nozzle. Now, ideally, the nozzle won't have any heat or work interactions. There's no moving parts that do significant work in the nozzle. And the air doesn't spend enough time in the nozzle to have significant heat transfer. So those two go away. And you'll notice since we have a 0 on the left-hand side, we can cancel the mass flow rate. And what we get is H6 plus V6 squared over 2 equals H5 plus V5 squared over 2. Now, one thing we typically do is if you look at the nozzle on the back of the jet aircraft, the velocity coming out of that nozzle is so much higher than the velocity coming in that we essentially neglect the kinetic energy coming in. So look at your schematic again on page 311, and this will make sense. The entrance to the nozzle is the exit from the turbine. It's not going to be moving, the air's not going to be moving super fast, so there's not going to be a whole lot of kinetic energy in it after it comes out of the turbine, okay, because the flow area is so large. The nozzle necks down a lot so that the flow area is decreased significantly so that you have a very high kinetic energy coming out, okay? So basically, we could rearrange this equation to solve for the velocity at 6. What would we have to do? Well, let's see, we need to get H5 less H6 on one side of the equation, multiply by 2, right, to take care of the denominator there, and then take the square root. That would give us V6. Again, if we were to use Cp delta T, then now we've changed the problem into something that we know, right? Because we know the temperatures at states 5 and 6. We solved for those earlier. So this would be the square root of 2. What was the heat capacity of air again? 1.005. Yep. Kilojoules per kilogram per Kelvin. The temperature at state 5 was 1150. The temperature at state 6 is 718. Both of those are Kelvin. So Kelvin goes away. And we have kilojoules per kilogram. Now, how would you like it if the speedometer on your car measured your speed in square root of kilojoules per kilogram? Would you have a nice, good, intuitive feel for that? Me either. Is there a conversion factor to get us to something that is more familiar, like a distance per time? Look in the front of your book. Had you either write this in or highlight it. Conversion